A buffer solution is going to be a solution in which we have significant quantities of a conjugate acid-base pair. We might have a weak acid, and we add the salt of the weak base, which would be, give me the conjugate acid-base pair, or the other way around for a weak base, weak acid. So we're going to have a conjugate acid-base pair with each added in, not the normal just dissociation of a weak acid. That's not enough of the conjugate base. Okay? Significant quantities of conjugate acid-base pair. If that's true, we can use the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation says that the pH is equal to the pKa plus the log of the base concentration over the acid concentration. The pOH is going to be equal to the pKb plus the log of the acid concentration over the base. So whichever way I want to do the calculation, I'm just flipping the acid and base relative to whether I'm using the pKa or the pKb. You might say, well, what is the pKa? pKa is negative log of the Ka. Nice thing about the pKa is it is the pH if the conjugate acid-base pair concentrations are equal. So if we have equal concentration of a conjugate acid-base pair, the pH is always equal to the pKa, and the pOH is always equal to the pKb. Okay, so what is the pH of a buffer solution with 0.25 molar HF and 0.1 molar NaF? Well, I've got to recognize Na is my spectator ion, doesn't influence the pH whatsoever. So I have a conjugate acid-base pair, HF and F minus. I know the Ka of HF, so I can calculate the pKa. pKa is going to be equal to negative log of the Ka, which is going to be 3.14. Okay, so now I can calculate my pH. The pH is going to be equal to the pKa, which is 3.14, plus the log of, since I'm working with pH, the base is on top. So my base, I'm going to write it out without the numbers first. My base is F minus. That's my conjugate base. Then on the bottom, I'm going to have HF concentration. So that's going to be 3.14 plus the log of 0.1 molar is the F minus. And then on the bottom, it's going to be the HF concentration, 0.25. Go through and do that calculation, and I'm going to get a pH of 2.74. You say, well, does that make sense? Yeah, you can always tell relative to the pKa the shift. If I have more of the acid pair piece of the pair, which I do here, I have more acid than I have the conjugate base, then I'm going to push down relative to the pKa. If I had more of the conjugate base, I would push up above the pKa. So I can always look at the pKa, it tells me the middle, when these concentrations were exactly the same. So if I had 0.25 molar HF and 0.25 molar NaF, the pH would be 3.14. Okay. Over here I have what is the pH of 0.01 molar ammonia solution. There's a conjugate, there's a base, weak base, with 0.2 molar ammonium chloride. Chloride is going to be my spectator here. I've got ammonia, ammonium ion combination. So that's a conjugate acid-base pair. I know the Kb of my base. I can calculate the Ka if I wanted to, or I can use the pH expression. the pOH expression. I'm going to use the pOH expression. But if you want to use pH, you just find the Ka of ammonium ion. pOH is going to be equal to the pKb, which is negative log of 1.8 times 10 to the minus 4. That is, let's write that up separate. pKb equals 4.74, negative log of this value. So right here we're going to have the pKb, 4.74, plus, since we're working with hydroxide, acid's going to be on top. So let's go ahead and write it out. NH4 plus over NH3. We have the ammonium concentration, and you know what I did? I left off my log. Let's erase that and fix that. Log of the ammonium concentration, the acid piece, over the ammonia concentration, the base piece. Well, now I can plug that in. 4.74 plus the log of concentration of the conjugate acid is 0.2. I'm going to have 0.20 divided by the concentration of the base, which is 0.01. Now, looking at it before I do the calculation, I have more of the acid component than I do the base. So I'm expecting the pOH to go up or the pH to come down, whichever way you want to think of it. But this, I'm calculating pOH. So I go ahead and plug this in, and the pOH is going to equal 6.04. Now I'm going to back calculate the pH from 14 minus 6, and I'm going to get 7.96. Okay? So, if the pKa is 4.74, then the pKb is 4.74, the pKa was 9.26. And you can see we become more acidic relative to that value, because we have a higher acid piece concentration than we do base in our buffer.